Let's take a look at chapter 4. It is on linear second order differential equations. And we'll go on to, so 4.1 is kind of their justification of why we might study, or the book, how they develop things, how we might study, or why we might study the system. What that brings us to saying, like, you're modeling a system, so you get these type of equations. So it kind of is justification for why we would look at these equations in the first place. So technically and you'll see this in the book, what we're going to look at is linear second order ordinary differential equations with constant coefficients. That's kind of the first, 4, 1, 4, 2, 4, 3. And then later we'll look at non-constant coefficients. But essentially it's the second order differential equations that we'll be looking at. So take a look on your own, 4.1, kind of how they develop the mass spring system. And then they use that analogy for the equation throughout the book. So, well, especially in this chapter, I guess. So the basic form then that's developed is this, that you have with constant coefficients, you have a y prime plus by prime, excuse me, ay double prime plus by prime plus c equals a function of t. And you could write that as like a dy dt, and but the second derivative, like right here. So in the analogy to the mass spring system, you could get this differential equation where the coefficient of y double prime is inertia, coefficient of y prime is damping, and the coefficient of just y is the stiffness of like the spring. And then you could have equal to an external force, which would be something like pushing on the object or something like that. We're going to get into, a bit more later in the class, the applications to more stuff. I haven't done a lot of that, much at all. So we will look at more applications towards the end of the class, once we've developed more techniques of solving the differential equations and getting kind of used to the terminology and used to the way the functions look and equations look, just the way I decided to do it this time. So we're going to continue. We'll look more into the details of solving them in 4.2. So 4.2 is on so the homogeneous case. I was going to make that up, is set equal to 0. So we're going to look at the basic system, ay double prime plus basic equation plus by prime plus cy equal to f of t. So that's your standard, form. And then we'll look at, for first couple sections here, 4.2, 4.3, the homogeneous case, which is a double prime plus by prime plus cy equal to 0. So that's generally how you state the homogeneous cases. So that's the form. Okay. So if you look at this form, we're looking at a derivative equaling to basically something times b, and you want to add all these up and get 0. So with a little bit of prompting, you might guess that let's look at this possible solution. So if you consider, so let's consider the equation or solution in the form of y equal to, okay, maybe just a little bit of prompting. What derivative gives you a constant times a function, and it doesn't change much as you do its derivative. So what derivative is basically itself, but then you might get a constant in front each time you take its derivative to make it more simple. And you know, with a little bit of prompting, we might guess it. So we're going to look at the solution to be e to the RT, because every time you take its derivative, if r is constant, then you get the constant times its derivative, and then that doesn't change. Like if you did a polynomial, eventually you get 0. We don't want that to happen. So we're basically guessing at a solution. It will work, of course, and then we derive the rest of it off of that. So it's kind of a strange way to start, but it's kind of how it works. So if you substitute that in, then go take a second to make sure these work, but you get a r squared as the double prime, e to the RT, plus b r e to the RT for the first derivative, right? R comes in front, plus c e to the RT equal to 0. And then all we have to do is we can factor out this e to the RT. Okay, so factor out e to the RT, and you're going to get, oops, I wrote that wrong. So you factor out that, and you get e to the RT, and you're left with ar squared plus br plus c equal to 0. Now, we have that for e to the RT, regardless of r or t, we know that is positive. So e to the RT is positive. It's never 0, and it's always positive. So because it's never 0, you can just divide out by that e to the RT, and you're left with a, b, and c as a polynomial, as a quadratic, right? So you divide that out, and you get this. You get a r squared plus br plus c equal to 0. That is what's called the auxiliary equation, or characteristic equation. Move that over a little bit, give myself some room. So auxiliary equation, or sometimes referred to as the characteristic equation. And we can always find two roots of that, right? We all know that. That's a polynomial, second degree to quadratic. And you use a quadratic formula to get your roots. So, and you always get them, right? I mean, they're guaranteed. They may be complex. They could be irrational. You could get a repeated root, but you will always get two roots, possibly repeated. So, so roots can be found by factoring. Okay, if it's easy, you know. Or we always have the quadratic formula. So we're guaranteed to find r as root. So once you find r, then basically you go back in to here and you plug it in, and you have just found your solution. So let's take a look at that. I wrote down the equation. So R1, R2 is equal to the quadratic formula, as you know, is minus b plus or minus the square root of b squared minus 4ac all over 2a. And then just to review a bit here, because this will come up as we go, if the radicand b squared minus 4ac is greater than 0, right, so it's positive, the discriminants, the other way of, it's the radicand of the of the square root, but it's also called the discriminant. Okay, so if b squared minus 4ac is greater than 0, we have two distinct roots. Meaning you're going to get, it's going to be non-negative, so when you do plus or minus, you're going to get a, plus 3 and minus 3, or plus root 5 minus root 5. Okay, and then if the root is, it's like a perfect square, so if b squared minus 4ac is a perfect square, then you'll get two distinct rational roots. Okay, and not that it matters, but that's what you'll get. Just kind of remember some of that stuff. So if b squared minus 4ac equals 0, then we have two repeated roots. So we have still two, always two, but we have two repeated roots. That'd be like factoring x minus 2 times x minus 2. It's still two of them, but it's just they're not distinct. All right. And then lastly here, if b squared minus 4ac is is less than 0, then what kind of roots do you have? So then we have two complex roots. And I'll say and are, so and are complex conjugates if, like it's an if and only if, so if and only if not if and only, it's an implication. So if A, B, and C, actually it is, I won't get into that stuff. Complex conjugates, it's still an implication. If A, B, and C are real. So when you're solving any polynomial of with real roots, when you get a complex solution, you always get its conjugate. So if you have, they use alpha beta because they already have A, B, and C in there. So if alpha plus beta I is a root, then alpha minus beta I is another root. All right, so those are roots. If that occurs every single time, if A, B, and C are real, the coefficients of the equation, right? So we're not dealing with coefficients that are not real. They're constants, but those are supposed to be real. And perhaps later you will look at that, but for now, that's what we are assuming. Okay, and we look at that in 4.3. Okay. So let's look at just an example to solve of how you would use this. And then we'll look at a little more of the theory stuff. So look at this example. This is number 2 in this section. So solve y double prime plus 6y prime plus 9y equal to 0. So what you do, and I'm kind of glossing over a lot of this stuff, in terms of how to do the derivation, but what you do is you do this, we know the solutions are going to look like this. So with your R here, basically what you do is you take this and plug it back into R, and that's your solutions. Those are your solutions. So this is really what you're solving. You take the characteristic equation and solve it. So the characteristic equation exactly matches the double prime and the R. So you put those as coefficients. So you basically just rewrite R. So this is the This is the characteristic equation where you have r squared plus 6r plus 9. So right, it's 2, 1, and then it'd be like r to the 0. Is how you're interpreting that. So it's the prime matches the power for that for r for the equation. And that's equal to 0. And then this is simple to factor. You just factor this thing, and you get r, and it's going to be 3 and 3. So r plus 3, r plus 3. So that case above would, of course, just be this. You get a repeated root. So r equal to -3 is a repeated root, like twice. Multiplicity is a term we would have used in algebra. So the multiplicity of that root is 2. I often use p for multiplicity. So p equals 2, often called multiplicity. But we're not getting much higher than 2 or 3, so we don't really talk about multiplicity of roots higher than 2, 3. I don't think we're doing 4. So if that's r, then e to the rt is the solution, or e to the -3t is that distinct solution. And you can check that. If you plug that in here, you'll get, you take the derivative, you get the -3 in front, right? 9 times that, -3 in front, and then you do it twice, you get the positive and add it all up, and you'll get 0. So you can check it real easily. Let's do another simple one before we move on. So this is number 4. So try this one. Solve y double prime minus 5y prime plus 6y equal to 0. So try r squared minus 5r plus 9r equal to 0. Okay, so I always like to do this so you see it. Try it. Okay, so you factor it. This one is nice and easily factorable. So r and r, and then you get oops, there's no r there. There we go. Oh, I totally wrote that wrong. Should be plus 6. Try that again. Okay, so you get r squared minus 5r plus 6 equal to 0. So you factor that thing. So you get r and r, 5 and 1, and they are both negative. So you get r equal to 5 or r equal to 1. And then your solutions are, so it's e to the rt, so your solutions are just going to be e to the 5t and e to the t, just like that. Okay, and again, so in this case, they're both two different distinct solutions. So you plug this in, do this calculation, and you'll get 0. Then you plug this one in, do this calculation, and you'll get 0. Okay. So that's kind of the, brute force, go for it. Here's your solution. But then now we got to talk about, okay, what's the general solution? When do you get to what happens in each case? We'll look at the complex conjugates, what you get, and that's actually a whole other section. Okay, so next we'll look at theorem 1, definition 1, theorem 2, and I'll actually look at some proofs. So this will get a little more theory based, and then we'll get on to some more examples.